how do you measure the immune health of 50,000 birds at once? You don't test them all. Pulling just 23 to 30 blood samples provides enough data to model the entire population. This is the foundation of avian serology, the study of how antigens and antibodies interact in vitro. Simply knowing an antibody exists in those samples isn't enough. Pathologists must quantify the exact concentration to gauge the flock's actual defensive strength against a virus. A flock's survival relies on converting those microscopic interactions into an actionable map of population immunity. The industry standard for quantifying these microscopic antibodies is the enzyme-linked immunosorbent assay, or ELISA. It is built for volume. Modern automated ELISA systems process 92 different serum samples in approximately 2 hours. ELISA's primary advantage is sensitivity. It detects antibody concentrations far too low for classic agglutination tests to catch. Commercial avian testing kits utilize two different biochemical strategies, the indirect format and the blocking format. This combination of automation and sensitivity turns ELISA into a practical instrument for daily agricultural management. This diagram illustrates the first step of an indirect ELISA, coating a bottom of a plastic well with a specific pathogen antigen. When the chicken's blood serum is added, disease-specific antibodies drop in and bind directly to those antigens. After a wash phase, a conjugate is introduced. This is an enzyme-labeled anti-chicken antibody designed to lock on to that first layer. Finally, a substrate reacts with the bound enzymes to create a soluble blue product. This reaction generates the core metric, optical density, or OD. The darker the blue, the higher the concentration of antibodies. In this format, a stronger visual reaction directly equals greater immune protection in the bird. This animated diagram shows the blocking ELISA, which operates on the exact opposite visual logic. An enzyme-labeled conjugate is introduced to actively compete against the chicken's own antibodies for the same antigen binding sites. If the chicken has a high antibody concentration, the conjugate is blocked from attaching and is washed away. When the substrate is added, the lack of enzyme means the liquid remains clear. In a blocking test, a lower optical density proves a much higher concentration of protective antibodies. Chicken anemia virus, or CAV, utilizes this format, identifying infection when the ratio falls below 0.6. Clinicians must immediately identify which format they are using, otherwise a clear well could be misdiagnosed as a vulnerable bird. Raw optical density numbers require flock metadata to have any clinical value. Accurate inference depends on variables like the age of the birds, the production line, and the hatching dates. The flock's vaccination program must also be encoded into the analysis. Without environmental and historical data, the statistical inference of a flock is impossible. This table shows how laboratory software scales raw OD numbers into standardized titer groups, typically across 18 categories. These groups are then plotted onto a 2D histogram to visualize the distribution across the entire population. In an ideal scenario, the cases cluster symmetrically around the average, forming a Gaussian or normal distribution curve. The curve's geometry immediately reveals the stability of the herd's immunity. Veterinarians use geometric mean titer to estimate the average severity of changes, as it reflects the biological distribution better than a simple arithmetic mean. But a high mean titer is misleading if it masks a dangerously polarized flock. This statistics report highlights the coefficient of variation, or CV percentage. A CV of less than 40% indicates a uniform flock that responded identically to a vaccine. High average antibody levels are compromised if the coefficient of variation is too high, as it exposes hidden vulnerabilities within the population. High statistical variance creates a crisis when scheduling a live vaccination for infectious bursal disease, or gumboro. This variance often occurs when hatcheries mix chicks from different parent flocks, each carrying different levels of maternal immunity. This side-by-side comparison shows the difference between a well-protected, uniform flock and the erratic distribution of a poorly mixed one. If variance is high, early vaccination wastes doses on immune chicks, while late vaccination leaves weaker chicks exposed to field viruses. Serology maps mathematical variance to pinpoint the exact window of opportunity for medical intervention.